All right, question 3. We've got a violin, and it's showing the tuning pegs, the bridge, and a fixed end A. So we can increase or decrease the tension in the strings. This is almost certainly going to be a standing waves question. So explain how a standing wave is produced when the string is plucked. Okay, so we're probably going to have to talk about so you're going to have to talk about the fact that a wave is reflected. So when you pluck it, you're causing a vibration. So plucking it is going to cause a vibration. What you're going to need to talk about as well is that when the wave goes to the boundary, so cause a vibration or a wave, okay? The waves reflect at a boundary. And waves can superpose. Okay? Be careful, because superimposing is something different. So I'm having to look this up. Superposition, so when things are superposed, you cannot tell what each thing contributing to it, what it's contributing. You only see the end product. A superimposition, you see the end product, but you can see individually what each component is providing. So you can separate it based on it. So with waves, we can't tell what wave is contributing what, if anything. Okay, but it's so it's superposition. Okay, so here you know that where it's fixed, that's a node. Okay, because they cannot move. Okay, and it will vibrate at its it will create a standing wave in this case. So you'll have constructive interference. So you'll have destructive interference. Or you will end up with positions of maximum amplitude. So you're going to have constructive interference where you've got the antinodes. Okay, so really they're just asking, how does a standing wave get made? So here, a vibrating length of one string is 0.33 meters. The tension is 25 newtons. The string vibrates with the first harmonic and a frequency of 370 hertz. It's saying show that the mass per unit length is 4 times 10 to the minus 4 kilograms. So that is mu. So F is 1 over 2L square root of the tension divided by the mass per unit length. So Sorry, all right. So mu, rearranging this, is T over 4 L squared F squared. So tension was 25 newtons. And what was the frequency? 370 hertz. And so that's 0. Just remember that for a show that, you always have to have one extra significant figure, minimum, in your answer, so that it's showing that you've actually done the calculation correctly. So determine the speed at which the wave travels along the string when it vibrates with the first harmonic of this. So C equals lambda F, and in this case, lambda equals 2L. Okay, so that'll be the trap there, that lambda is 2L. So C is equal to 2 times 0.33 times 370. $244, which is 240 meters per second. 2 sig figs everywhere. So this shows how the tension in the string varies with the extension. Okay. Okay, so we have to find out the extra extension. So the extra extension, what we have to do is look at it like this. So it's extending, so we're going and moving it through this. That's 75 degrees. So you have to do that, convert it to radians by dividing by 2 pi, and then multiply it by the radius. So 7.02 divided by 2 times 75 divided by 2 pi. It's 41. No, that's not right. Divided by 2 pi over 360. No, okay, nah, bad. Okay, 75 divided by 360 times 2 pi. There we go, 4.59 millimeters. So it was at 25 newtons. Okay, which is 11. So I have to go to 15. .6, which is going to be about right here. So 35.5 newtons. So change in extension. I'll write down what I would expect to see. So change in extension is equal to d over 2 times, I'm just going to put my numbers in. 7.02 over 2 times 75 over 360 times 2 pi. That's just to get the arc length. Okay, that was 4.6 millimeters. So the new tension, 35.5. Frequency equals 1 over 2L square root of T over mu. .5 divided by, what was mu? 4.2 times 10 to the minus 4. .440 hertz. Okay, so 440 hertz. And that is it for this particular question.